Hello everyone, welcome back. Today, we are diving into one of the most critical components inside your computer, cache memory. Now, before we get technical, let me ask you, why does your computer feel fast? Is it just the processor? No. The truth is, the most powerful processor in the world is useless if it spends its life waiting. In the early days of computing, as processors became faster and faster, engineers discovered a massive fundamental problem. The CPU was becoming a sports car on a dirt road. This is the perfect analogy. Imagine you have a Ferrari engine that's your CPU, but you are driving it on a bumpy, muddy dirt road. That's your main memory, or RAM. It doesn't matter how fast the engine is, the road slows you down. This gap between the super fast CPU and the slow RAM created a crisis known as the memory wall. The CPU was getting faster every year, but RAM couldn't keep up. So, engineers needed a bridge, a solution, and that solution is cache. Here is the trade-off we face as engineers. We want memory that is fast, big, and cheap. But in reality, you can't have all three. Fast memory is expensive. Big memory is slow. Cache is the brilliant compromise. To truly understand cache, let's look at this CEO analogy. Imagine the CPU is a hyper-efficient CEO who signs 1,000 papers a minute. But the documents are stored in a massive archive room, that's your RAM, way down the hall. If the CEO has to wait 10 minutes for an intern to fetch every single paper, they sit idle all day. This is called stalling. So, the solution? The CEO puts a small briefcase or desk drawer right next to them. This is the cache. Before the day starts, they grab the files they are most likely to need and put them in the briefcase. Now, they can reach in, grab a file in a split second, and keep working. They only go to the archive room when absolutely necessary. This is exactly why we dive into cache. Now, technically speaking, cache memory constitutes a small, high-speed storage component designed to retain frequently accessed data and instructions, thereby enhancing a computer's operational speed. It functions as an intermediary buffer situated between the central processing unit and the comparatively slower main memory, RAM, facilitating significantly faster data retrieval by prioritizing a check of the cache. By maintaining proximate storage of common data, cache memory mitigates the necessity for the CPU to access main memory, which consequently yields substantial improvements in performance. So, simply, cache is a small, high-speed buffer between the CPU and RAM. But how does the cache know which data to put in that briefcase? It can't guess. It relies on the principle of locality. This is the golden rule of caching. There are two types, and let me give you a real-world example for each so you never forget them. First, temporal locality. The notes say if a datum is accessed, it will likely be required again. Think of this like a song you are obsessed with. You play it, and then you hit replay immediately. The computer does this with loops encoding, checking the same counter variable over and over. The cache keeps that variable close by because it knows you just used it. Second is spatial locality. The notes say if a datum is accessed, contiguous data will be required. Think of watching Netflix. If you watch episode 1, what are you 99% likely to watch next? Episode 2! You rarely jump from episode 1 to episode 10, so the cache preloads the next data, assuming you will need it. Now, let's see this in action. First, the CPU asks for data from a specific memory address. Then, the request is intercepted by the cache controller, which checks the high-speed cache memory to see if a copy of the requested data is already stored there. Now, a cache hit occurs when the requested data is successfully found within the cache memory. The data is retrieved immediately from the cache, typically in 1 to 2 nanoseconds, and sent directly to the CPU. This is the ideal scenario, providing the CPU with data at maximum possible speed and allowing it to continue processing without delay. But what if the data isn't there? A cache miss occurs when the requested data is not found in the cache memory. This results in a significant time delay known as the miss penalty. Here, the CPU has to wait until the cache controller fetches the entire block of required data from the much slower main memory, and then that is written into an empty or an existing line in the cache. Finally, the requested data is forwarded from the cache to the waiting CPU. For all of this, the CPU experiences a substantial delay of 100 nanoseconds or more. Here, the job of engineers and programmers is to write code that maximizes hits and minimizes misses. A miss is expensive. Now, you might be thinking, okay, I get the concept, but does this little box of memory really make a massive difference? Let's prove it with math. We use a metric called EMAT, effective memory access time. Think of this as the average time the CPU waits for data. Before we see the formula, we need to define our variables. First, we have the hit ratio. This is your success rate. If you look for data 100 times and find it in the cache 95 times, your hit ratio is 0.95. That means the miss ratio is simply the opposite what's left over. So 1 minus h, or 0.05. Now, cache access time is the time to access the cache, also called hit time. And main memory access time is the time to access main memory, also called the miss penalty. Now, how do we calculate the average speed? It's a simple weighted average. We combine the time we spend on hits with the time we spend on misses. Look at this example here. If we have a 95% hit ratio and the cache takes 1 nanosecond while RAM takes 100 nanoseconds. And what is the result? 5.95 nanoseconds. Look at that result closely. The main memory takes 100 nanoseconds to respond. But because of our cache system, the CPU feels like the memory takes just nearly 6 nanoseconds. We've achieved a speed up of over 16 times. We effectively hid the slowness of the main memory. This mathematical proof is why we spend so much money and effort optimizing cache. It's the only way to keep modern processors fed. Now, we arrive at the most interesting engineering challenge. We know cache is fast, but it is also very small, maybe 4 megabytes. Main memory is massive, maybe 16 gigabytes. So, here is the question. How does the cache keep track of which pieces of data it currently holds? It's like trying to find a specific needle in a haystack, but you need to find it in 1 nanosecond. To solve this, we need a very specific organization. We don't just throw data in there randomly. First, we need to understand our units of transfer. The CPU usually wants a word, a small piece of data, like 4 bytes, to do a calculation. However, the cache hates fetching small things. When the cache goes to main memory, it grabs a whole chunk called a block or a cache line. A block typically holds multiple words, for example, 64 bytes. Now, just understand again that why do we fetch a whole block just to get one word? This is a gamble on spatial locality. Imagine you are at a library and you need volume 1 of an encyclopedia. You wouldn't just take volume 1. You would grab the whole set, volume 1 through 10, and put them on your desk. Why? Because if you needed volume 1, there is a high probability you will need volume 2 next. The cache does the exact same thing. It prefetches the neighborhood of data to avoid going back to RAM later. So, what does the cache actually look like in hardware? It is essentially a hardware array, a lookup table. Every single row in this table, called a line, has 3 specific components. 1. The data store. This is the actual 64-byte block we copied from memory. This is the payload. 2. The tag store. This is critical. Since the cache can only hold a tiny fraction of main memory, many different memory blocks could technically fit into this one slot. The tag acts like an ID card or a label. It tells us which specific block from main memory is currently sitting here. 3. The valid bit. This is a simple 0 or 1 flag. When you first turn on your computer, the cache chips are powered up, but they are full of random electronic noise or garbage data. We can't let the CPU read that. So, initially, all valid bits are set to 0 to mean invalid. Once we load real data, we flip this switch to 1. It basically tells the hardware, this slot is occupied with real data. Now, this is the part that confuses most students, so look closely. How do we find data? When the CPU sends an address, like 32 bits, the cache hardware splits that address into 3 distinct parts to navigate the cache structure. First, the index. This answers the question, which row should I check? Think of the index like a hotel room number. If the index is 5, the hardware goes directly to room or line 5. It doesn't search the whole building, it goes straight to 5. Second, the tag. This answers the question, is this the right guest? Just because we went to room 5 doesn't mean the data we want is there. Maybe a different memory block is currently staying in room 5. So, the hardware compares the tag in the address with the tag stored in the cache line. If they match, we found it. Third, the offset. This answers, which byte do I want? Remember, we fetched a whole block of 64 bytes. The CPU might only want byte 4. The offset tells the hardware exactly where inside that block to grab the data. Now, let's put it all together in a rapid fire sequence. Here is what happens in nanoseconds when the CPU asks for data. The CPU sends the address, hardware extracts the index and jumps to that specific cache line. It checks the valid bit. If it's 0, stop. That's a miss. If it's 1, it compares the tag. Does the ID match? If no, stop. That's a miss. If the tag matches, bingo, it's a hit. Finally, it uses the offset to slice out the exact word and send it to the CPU. This elegant dance of bits happens billions of times per second in your phone or laptop right now. This structure allows us to find one specific byte among gigabytes of data instantly. So, let's wrap this up. Today we learned that the CPU is a Ferrari and main memory is a dirt road. Without help, that Ferrari stalls. Cache memory is the bridge. It uses the principle of locality to predict what you need and keeps it close, effectively hiding the memory wall. So, now, why does this matter to you? Why should you care about cache? Why does knowing this make you a better engineer? Let's talk about game development. Have you ever wondered how modern games like Assassin's Creed or Total War can simulate thousands of soldiers on screen at once without lagging? The secret is cache optimization. A lazy programmer scatters data all over the RAM. Every time the CPU wants to update a soldier's position, it has to jump to a random spot in memory. That causes a cache miss. The CPU stalls, waiting 100 nanoseconds. Do that for 1000 soldiers, and your game frame rate drops to 0. You get lag. But a smart engineer, one who understands this lecture, writes cache-friendly code, often called data-oriented design. They pack all the soldiers' data right next to each other in memory. Why? Because of spatial locality. Remember the block concept? When the cache fetches soldier 1, it automatically brings the entire block containing soldier 2, 3, and 4. And the result? 0 stalls. The CPU processes the whole army in one smooth, lightning-fast sweep. This is your superpower. If you understand how the hardware thinks, you don't just write code that works, you write code that flies. That is the difference between a junior developer and a lead engine architect. Next time, we will look at mapping techniques to see exactly how we organize these blocks. If you're ready to speed up your learning, hit that subscribe button. I'll see you in the next lecture.